Hello dear students, today we are going to start a new chapter, that is P block elements. We studied already this chapter in plus 1 regarding group 13 and group 14. In detail we studied both the groups. Here today we will discuss, or in this chapter we are going to discuss group 15, 16, 17 and 18 in detail. Today we will discuss about group 15 elements. Group 15 elements are usually called as nitrogen family, and the elements are nitrogen, phosphorus, arsenic, antimony and bismuth. We will first study the general characteristics of the group 15 elements. The elements are nitrogen, phosphorus, arsenic, antimony and bismuth. Bi. Okay, nitrogen, phosphorus represented by P, arsenic, antimony and bismuth. Okay, this Sb is antimony. These are the group 15 elements, and the atomic number of nitrogen is what? 7. Phosphorus 15, arsenic 33, 51 for antimony and 83 for bismuth. These are the atomic number of elements for nitrogen, phosphorus, arsenic, antimony and bismuth. Note down. Next we are going to study what? The valence electronic configuration of these elements. We already studied this, isn't it? In our plus 1 chapter. Nitrogen is what? The outer electronic configuration of nitrogen is what? 2s2, 2p3. This is the outer electronic configuration. Phosphorus is what? 3s2, 3p3. Arsenic 4s2, 4p3 and antimony 5s2, 5p3. Similarly, bismuth is 6s2, 6p3. So we can understand from this what? The general electronic configuration is ns2, np3. Okay, ns2, np3 is the general valence electronic configuration, and the properties, chemical and physical properties, depend upon, or it also depends upon the valence electronic configuration. So due to their similarity in properties, we categorize them into groups, isn't it? Due to their similar valence electron configuration, that is ns2 np3. In the p orbital it is having what? 3 electrons. This is, okay, wait. This is the S. In the case of phosphorus, it is 3S and 3P. This is 3P. 3S2, 3P3. Okay, it is half-filled and highly stable. Nitrogen family elements, okay, their outermost 3P orbital is half-filled and it is highly stable. This much about the electronic configuration or the valence electronic configuration. Okay, from top to bottom we know that principal quantum number increases 2, 3, 4, 5, 6, isn't it? As a result, what happens? Number of shells also increases. That means the number of shells are increasing, isn't it? Down the group. So what happens? Atomic radii increases from top to bottom. That is, first we study the simple, then the atomic number. As a result of atomic mass increases down the group. Similarly, as the atomic number increases, mass also increases from top to bottom. Similarly, from top to bottom when we are moving, what happens? Atomic radii increases. As the number of shells increases from top to bottom, atomic radii increases. So number of shells increases from top to bottom, atomic radii, that is what? The distance from the center to the outermost electron increases. So atomic radii increases from top to bottom. Similarly, atomic number increases, atomic mass increases. Mass equal to, density is equal to what? Mass by volume. So as the density, mass increases, density also increases. Top to bottom, density increases, mass increases as the shells are increased. Next important property is what? Ionization enthalpy. What is ionization enthalpy? We studied earlier, isn't it? Ionization enthalpy is the amount of energy required to remove an electron from the outermost orbital. Amount of energy required to remove the most loosely bound electron from a gaseous atom is the definition. Okay. How much the nucleus has the ability to hold the outermost electron. It is the measure. Okay, ionization enthalpy is the measure of how much the outermost electron can be held by the nucleus. What is the trend? From top to bottom, ionization enthalpy decreases or increases? We studied, isn't it? As the number of shells increases from top to bottom, the outermost electron will be what? Away from the nucleus. So it is easy for, okay, as the force of attraction decreases, as the distance from the electron to the nucleus increases from top to bottom, force of attraction between this electron and the nucleus decreases. Okay, when distance increases, force of attraction decreases. As a result, we can easily remove the outermost electron. Not much energy is required. Ionization enthalpy is the energy required to remove the loosely bound electron. So from top to bottom, what happens? Or from nitrogen, phosphorus, arsenic, antimony, bismuth, from top to bottom, ionization enthalpy, okay, delta Hi, ionization enthalpy from top to bottom decreases, the energy decreases. Ionization enthalpy decreases. Similarly, what is electronegtivity? The energy that we can share, okay, the ability to attract shared electrons towards itself. The ability of an atom to attract shared electrons towards itself is called electronegtivity. Similar to ionization enthalpy, electronegtivity values also decreases down the group. Okay. So what is the order of electronegtivity? Electronegtivity is high for nitrogen, oxygen, arsenic, antimony, and then bismuth. This is the order of what? Electronegativity, first ionization enthalpy, but atomic radii order is what? Nitrogen less than phosphorus, arsenic, antimony, and then bismuth. Okay. Atomic radii order is this. Atomic radii increases from top to bottom. Similarly, atomic mass increases from top to bottom. Density also increases from top to bottom. But electronegativity value and first ionization enthalpy value decreases from top to bottom. These are the general trends of nitrogen family, that is nitrogen, phosphorus, arsenic, antimony, bismuth. Let's discuss a summary. We studied the electronic configuration. The general electronic configuration is what? Ns2np3. And the valential electronic configuration plays a major role in what? The behavior of the elements. General electronic configuration is Ns2np3. Next point is what? The s orbital in this group is completely filled and the p are half filled, and this makes their electronic configuration extra stable. Half filled configuration makes it extra stable. The second property is atomic and ionic radii. The addition of new orbitals increases both the atomic and ionic radii of group 15 elements. From arsenic to bismuth, only there is a small increase in ionic radius. It is because of the presence of completely filled d or f orbitals in heavier members. Third, we discussed about ionization enthalpy. It is the amount of energy required to remove an electron from the outermost orbit of an atom. Or it is to measure the how hard the nucleus is holding on to the last electron. The closer the electron is to nucleus, the stronger its hold, and thus the energy required is more. As we move down the group, the radius of the atom increases. and ionization enthalpy decreases due to its weaker hold of the nucleus. Okay, outer electrons weakly holded by the nucleus. The last property was electronegativity. The electronegativity value decreases down the group with increasing atomic size. It decreases with increasing atomic size down the group. This is due to what? Increasing distance between the nucleus and the valence shell as we move down the group. These are the These are the four main properties that we discussed. Next, about the physical properties of group 15 elements in common. They usually form polyatomic state. Okay, they usually exist in polyatomic state. The next property is what? First, nitrogen is gas. Okay, first element nitrogen is gas. Then as we move down the group, what happens? Metallic character of the elements increases. That is a physical property. Nitrogen is a gas and the other elements down the group, the metallic character of the elements decreases down the group. That is, nitrogen and phosphorus are non-metals, while the down the group, the arsenic, antimony are metalloids and bismuth is a metal. This is important. Nitrogen and phosphorus are non-metals, arsenic, antimony, metalloids, and bismuth is a metal. These changes are attributed to what? Decrease in ionization enthalpy and increase in atomic size down the group. Boiling points also increases as we move down. Boiling point increases as we move down. Okay, except for nitrogen, all other elements in group 15, phosphorus, arsenic, antimony and bismuth, all of them have allotropes except nitrogen, which is a gas. All other elements on the group 15 have what? Allotropes. Let's discuss the chemical properties now. The valence shell electronic configuration is Ns2Np3. That means it is Ns2Np3. Or the outermost electronic configuration is Ns2Np3 means what? It can either lose 5 electrons or gain 3 electrons to form what? Outermost configuration. Outermost electronic configuration is what? To form 8 electrons. That is Ns2Np5. Isn't it? Ns2Np3. This can either what? Release or lose these 5 electrons and take part in a reaction, or it can do what? Gain 3 electrons. Next, the common oxidation state exhibited by these elements are -3, +3 and +5. Okay, Ns2Np6 is the configuration. Okay, Ns2Np6 is the outermost configuration, or we can say Ns2Np6 is the noble gas configuration. To attain noble gas configuration, you can add +3 electrons, isn't it? Or what it can do? It can donate all these outermost 5 electrons. So, the common oxidation states are -3, +3 and +5. The tendency to gain 3 electrons create what? -3. Okay, or 3 minus we can say. When it has a tendency to gain 3 electrons, it is 3 minus oxidation state or -3 oxidation state, and that tendency decreases down the group. It decreases down the group. Okay, bismuth hardly or bismuth usually will not form -3 oxidation state due to what? Down the group, the -3 oxidation state decreases, tendency decreases. As we go down, the stability of what? +5 decreases and that of +3 increases due to inert pair effect. These are the chemical properties mainly regarding oxidation state. The main or the common oxidation state, please note down, it is important. Students, now let's discuss about the preparation properties and uses of dinitrogen N2. How it is prepared commercially, then in laboratory preparation, and also some other important methods of preparation. Let's first discuss how dinitrogen is prepared commercially. It is prepared by the fractional distillation. Okay, the liquefaction and fractional distillation of air will give you dinitrogen. Fractional distillation of air gives dinitrogen. Liquid nitrogen boiling point is what? 77.2 Kelvin, and oxygen is that of 90 Kelvin. Which will distill first? Okay, liquid nitrogen having lower boiling point 77.2 Kelvin will first get distilled, and this oxygen, liquid oxygen, will remain in that solution of air. This is how we will separate dinitrogen from air by fractional distillation. The one which is having lower boiling point will first boil, and that will distill out through the column, fractional distillation column, and we will obtain the remaining oxygen will be remained in that, and the distilled product we will use, dinitrogen product. This is the commercial preparation, commercial. In large quantities, how we will prepare, fractional distillation. Second method of preparation is the laboratory method of preparation. Here, aqueous ammonium chloride will react with sodium nitrate. Aqueous ammonium chloride reacts with sodium nitrate to give you dinitrogen plus 2H2O plus NaCl. Here you will obtain dinitrogen gas, but still it will have what? Impurities. Mainly the impurities in this dinitrogen gas are HNO3, nitric acid, and nitric oxide, NO. Okay, these two impurities will be still present. We can separate it by passing this N2 gas, obtained N2 gas, through an aqueous solution of H2SO4, sulfuric acid and potassium dichromate. Okay, then the impurities will get separated and you will obtain pure dinitrogen. Okay, this is the laboratory preparation. Aqueous ammonium chloride plus sodium nitrate will give you dinitrogen gas with impurities. That impurities like HNO3 and nitric oxide NO can be removed by passing the dinitrogen gas through a solution, aqueous solution of potassium dichromate and sulfuric acid. The next method of preparation is by thermal decomposition of ammonium dichromate. Thermal decomposition. Thermal decomposition of ammonium dichromate, NH4 twice Cr2O7, chromium dichromate. Ammonium dichromate on heating, this is a simple for heating, okay, like a triangle. On heating will give you, or under thermal decomposition, ammonium dichromate give you nitrogen gas plus H2O plus Cr2O3. Another method of preparation is the thermal decomposition of barium nitride. Okay, thermal decomposition of, barium azide, it is BaN3 twice. Barium azide, BaN3 twice on thermal decomposition will give you barium plus 3N2 dinitrogen. Barium nitride, or here you can use barium azide, or here you can use what? Sodium azide also. Barium azide and also sodium azide will undergo thermal decomposition to give you barium plus dinitrogen gas. Okay, barium we will precipitate out and you will obtain dinitrogen gas separately. These are the methods of preparation, the commercial method of preparation and then laboratory methods. 3 laboratory methods. First is the reaction with ammonium chloride and NaNO3. Then thermal decomposition of ammonium dichromate and also barium azide. The important properties and uses, let's study. Properties, main properties, the physical properties. It's a colorless, odorless, tasteless and a non-toxic gas. Dinitrogen is a non-toxic gas, remember that. Okay, colorless, odorless and also tasteless. Nitrogen has 2 stable isotope, okay, N14 and N15. N14 and N15 are the isotopes, 14 and N15. What are isotopes? Having same atomic number and different mass number. These are the 2 stable isotopes of nitrogen. Next property is the low solubility in water. Dinitrogen or nitrogen gas is not soluble that much, okay, it's a low solubility in water, Third point is what? Low freezing and boiling points. Boiling points and freezing point. Both are low. Dinitrogen boiling point and freezing point are low. We studied what? The preparation, commercial preparation, isn't it? Where we found the boiling point is what? 77.2 Kelvin. It has low boiling point and freezing point. Okay, also this dinitrogen is inert in nature. Inert means it will not fastly react. It is inert at room temperature. Why? Dinitrogen is inert at room temperature due to their high bond enthalpy. It has a high bond enthalpy. Dinitrogen exists as with 3 double bonds as N2. Okay, N2 is what? N triple bond N. It has high bond enthalpy. As a result of that, it is inert at room temperature. Inert. It is inert at room temperature. An important property of dinitrogen. Okay, it has high boiling point. Also, low solubility and low freezing and melting points. The reactivity is the next property. Reactivity usually increases with the increase in temperature, or reactivity increases with the rise in temperature. As a result, it forms ionic nitrides and also covalent nitrides at higher temperature. Okay, it is usually inert in nature, we studied. But at higher temperature, reactivity of dinitrogen usually increases. And it forms what? Ionic nitrides and also covalent nitrides. When metals and non-metals react, they usually dinitrogen at higher temperature forms what? Ionic nitrides and covalent nitrides. Look at the reaction. Lithium plus dinitrogen at a higher temperature on heating will give you what? Lithium nitride. Magnesium plus nitrogen, dinitrogen at higher temperature will give you magnesium nitride. Both these reactions are important. At higher temperature, dinitrogen forms what? Ionic and covalent nitrides. These are the main properties. Next important thing is what? It is used. Nitrogen reacts with hydrogen to form ammonia. We studied this in D block, isn't it? It is Haber process. N2 plus 3H2 will give 2NH3 at a higher temperature, that is 773 Kelvin. At a higher temperature of 773 Kelvin, dinitrogen reacts with 3H2 or with hydrogen at higher temperature to form ammonia, NH3. Then that process is called what? We studied. It is Haber process. Haber process is the manufacture of ammonia. Next property is what? Dinitrogen reacts with dioxygen. N2 plus O2 will give you nitric oxide. N2 plus O2. Dinitrogen reacts with dioxygen to form nitric oxide. These are the two important preparation methods of nitric oxides and ammonia. At a higher temperature, dinitrogen reacts with dioxygen and to form nitric oxide, and similarly Haber process is the manufacture of ammonia. These are the properties of dinitrogen. Now let's look into the uses of N2 or dinitrogen. As we discussed, it is mainly used in the what? Manufacture of ammonia. Okay, industrial preparation of ammonia is by Haber process. N2 plus 3H2 gives 2NH3. So the first use is what? Ammonia manufacture. Similarly, also manufacturing of compounds containing what? Ammonia. That is what? Calcium cyanamide, or compounds containing nitrogen is calcium cyanamide. In the preparation of ammonia and also what? Calcium cyanamide, dinitrogen is used. Next, due to the inert nature of dinitrogen, it is also used in what? Steel industry and iron industry. There, in steel and iron industry, manufacturing requires an inert atmosphere. Okay, in laboratories also, dinitrogen is used because there an inert atmosphere is required, or inert what? Inert conditions, laboratory conditions are required. So we use dinitrogen in iron and steel industry. Okay. The third and the last important use is the use of liquid dinitrogen. Okay, this is liquid dinitrogen. Liquid dinitrogen is used as what? A refrigerant. In cryosurgery, etc. As a refrigerant, we usually use liquid dinitrogen for preserving food items and other things, okay, biological materials, etc. For preserving that, we use liquid dinitrogen. These are the main important uses of dinitrogen. We studied the preparation, commercial, then what, laboratory preparations, and some other two important preparations we discussed. Then we discussed the main properties of dinitrogen and also the uses of dinitrogen. Each points are important, and note down these points in your notebook. That's all, dear students. I hope you understood. If you have any doubt, you can comment below. Thank you and have a nice day. Happy learning.